So that is the main topic. Okay. However, before we get there, we'll begin with an exercise. Okay. So let's take about 5 to 10 minutes for the exercise. So faculty members and DMS, JNTU and JNT Kakinada, please facilitate this exercise in your classroom there. Turn on your video, that way I can see. Take about 10 minutes. That will give time for others to join too. In the meantime, you would have learned something. Okay? Groups of 2. 1, 2, 3, 4, 5 questions. So 10 minutes. Okay? 10 minutes exercise as a group exercise. The first half of today's lecture would be kind of like a review of some of these things, the trees, binary trees, and then representation of the trees. We talked about representing them as lists, arrays. You may or may not remember, right? So it's always a good idea to always rehash what we learned. And then I'm going to point out what are some disadvantages of the binary trees with like a list representation. And to address those disadvantages, we have invented the concept of threaded binary trees. So this is all a build-up towards that. Okay? Okay, I will mute myself for some time while you are doing the exercise. And if you memorize the formula, right, you should be able to easily draw a quick binary tree and figure out some relationship between the nodes. Okay? Same thing, maximum number of nodes in a binary tree of depth k. So it allows you to recall what we mean by depth. Next, of course, for any non-empty binary tree, if you know the leaf nodes, the number, and then if you know the number of nodes of degree 2, so this allows you to recall what we mean by degree, okay? And what is the relationship between NO and N2. Then a quick recall of what a full binary tree is, right? And then what a complete binary tree is. And then in terms of the log value, what is the height of a complete binary tree. 10 minutes from now, we'll start the lecture. I want DMS to answer. I want Chaitanya to answer, ASET to answer, SVCW to answer. If you do not answer, I'm just going to move on because I just assume you hear me and then I'll move on, okay? Now, I got answers from Jntuk Kakinada to the questions of the exercise. You just have to do it on your own, okay? I usually give the first 10 minutes to 15 minutes to do the exercise. We have already given enough time today, okay? Here are the answers. Okay. 2 raised to I minus 1, I greater than or equal to 1, the first question. Second one is the maximum number of nodes in a binary tree is 2 raised to k minus 1. Now notice one thing here. When we talk about the level I or depth k, we have to know, it depends on what paper you read, right? The depth can start at either number 0 or depth can start at 1. And some authors, when we write the papers and all that, we say the very root node is at depth 0. But some authors, they call it as depth 1. So when this question is given, typically they give the I greater than or equal to 1 suggestion, question number 1, they're starting at depth, the root node is at depth 1. Okay? In some places I say the depth is greater than or equal to 0. That means I equal to 0. So you have to modify the formula accordingly, whether the depth is referenced as 0 or 1. Okay? Depth or level. Okay? Root is always at level 0 a lot of times. But in some of these formulas, in this case, root starts at level 1. Okay? So you got the answers there. And what is a full tree? Okay? We'll see that shortly. Okay? Full and complete, right? Now depth, students, as you know, is the maximum number of steps through ancestor nodes from the deepest leaf back to root. Okay? So, if you take that definition, tree with single node has depth 0 because you are not going anywhere, 0, right? And empty tree has depth of minus 1. Again, one more time I'll reiterate, it depends on how the author defines it, right? So if you look at the depth of this tree here, okay, is what? What is the depth of this tree here? Ancestor node from the deepest leaf. Deepest leaf is G, right? So you're taking 2 steps. So depth of the node from G to A is 2. D, E, F, and J are at the same level, right? So the depth is 2 here. Okay. You can also call 3, provided you consider A as depth level 1. Okay. That's why again it goes back to the reference point. Okay. Now in the tree, as you can see, if I say depth of B, the subtree B, it's 1. Depth of F, subtree. F has no subtree, right? Because it's the leaf node. Depth is 0. Okay. Okay. Full binary tree. Full binary tree, every parent has 2 children and every leaf has equal depth. Okay. Again, a lot of times I forget the definitions. I keep going back. Now I have done it a number of times. Maybe I'll remember it for 6 months now. Okay. Every parent has 2 children and every leaf has equal depth. Okay. That is 2 conditions. Okay? Remember that. Now in contrast to that, if you look at a complete binary tree, it is full except possibly at the deepest level. Okay? Full meaning they have children. So here in this case B, it has children. Okay? And then at the deepest level, if you look at the branch AC, okay, there is no there are no children, but the condition leaf nodes are as far to the left of God, right? So D and D are left of C. So we covered this example, if you recall, from our class, right? Let's put the answers there. I don't have to ask you the question. You can see complete binary tree on the left. Okay. It is complete but not full on the left because if you see B, B does not have two children. Okay. There is one in the center here. It's a full and complete. Okay. And neither, both, like that. So you should keep doing a lot of examples related to this because these are legitimate examples. Okay. Now, in order to understand threaded binary trees, we need to go back and revisit some of the concepts of trees and how they are represented. Okay. So that is what I'm going to be talking about next. So we know what a tree structure is. Okay, here is another way of looking at tree structure. It's a hierarchy. Okay, remember, trees do not have cycles. You will not have something going from leaf to the parent, right? As such. So here is one example. Okay. We know the definition of a tree, where I will not repeat that one. Okay. Important point to note: every node in the tree is a root of some subtree. So leaf node is a root by itself, right? So subtree it's a subtree of one. To look at the recursive definition of a tree. Good to remember some terminology. We know node. Degree is the number of subtrees of a node. Okay. And then the degree doesn't have to be the same for the tree, right? Some subtrees may have different degrees. That's why we call degree of a tree also. Whatever is the maximum of the degree of the nodes in a tree, that is the degree of a tree. And we did exercises in the past when we covered trees, what degree, depth, and all that. Okay. Rest of the terms are pretty straightforward. Okay. Sibling, same level, ancestor, level, Okay. If root is at level 1, if a node, then if the node is at level L, then its children are at level L plus 1. Height is the maximum level of any node in the tree. Okay. So we covered this example before. Here is a nice example. Good morning, SV Sirabia. I'm able to see your video now. So as you can see here, this picture that we covered before shows all the concepts here, right? So if you look at the degree here somewhere, degree of B. The degree of B is 2 because it has two subtrees, two children, or two subtrees. Whereas the degree of C is 3 because it has 3 branches coming out, right? So when you talk about the degree of a tree, degree of a tree is defined as the maximum degree of any of the nodes in the tree. So in this case, the maximum degree is 3 because node C has degree 3. Okay. Okay. Now we get into a little bit more detail. We talked about representation of trees in the past, right? We talked about representing tree as a list, array, right? So let's look at that, right? Interesting concept. The reason I wanted to revisit this one is it's very hard to remember these things unless we keep repeating them periodically, right? Because with that intent, I'm covering this again towards build-up of the threaded tree. Okay. So here is a tree given on the right side, right? This is that figure 5.2, by the way. You have A, B, C, D, E, F, G, H, I, J, K, L, M. Now, if you notice here, in this case, the author represented root A as level 1. Okay. So since it's level 1, next is 2, and so on. If that was represented as 0, then it will be 1, 2, 3. Okay. Now, list is a list, right? So we covered what the concept of a list is. So enumerated values, that's what a list is in one way. So here he's representing the list. As you can see how in parentheses, the way he's writing it, the root is coming first, followed by a list of subtree. Okay? That's one way of representing a list. Okay? You see on the figure 5.3, so you have the data, and then you have all the links. Links correspond to the subtrees of that data. Okay? So how do you interpret this from this to this parenthesis thing? How did we come up with that? That is the question, right? So A is the root. Okay. A has B as one of the siblings, right? Linked to the subtree, right? Now, and then B has a whole bunch of things underneath them. So those are in parentheses. We'll come back to that. Then you have C, so immediate links, right? C has something underneath that which is parentheses. Got it? And then you have D. Put some parentheses around it. Now, if you expand the B list, then what does B have? B has two subtrees, E and F. So you put E, put parentheses, comma, put parentheses. Parentheses are important. That's how the system would interpret which of them are sub-branches, right? Okay. Now, continuing with the B part, we'll go inside that. B has E, right? E has K and F. That's so E, parentheses, K. F has nothing. Okay. When you go to C, C has G. If you go to D, you get H and I. So you have H, parentheses, I, and then you get J also. And wherever you have parentheses, you expand till you go to those. That's how you build the list. Okay. So if I were to give you if I were to go back to the previous picture here, take any of the pictures, right? So in this case, let's say if you take the picture A, B, C, D, you can practice that list structure here. Not right away. Some way how to draw the list. It's again a legitimate question to be given in an exam. Okay. So that is the list representation. Any questions, comments on that? If any faculty member wants to expand on what I just said, please let me know. I can pass the ball to you. Okay. That is one way of representing a tree. Again, we kind of covered these things and readdressing them, so that way you will start internalizing that in your brain. You can also represent it the other way. Okay. The other way here is called the left child, right sibling. So you can see the data structure in 5.4 here. You have data, then you capture the left child of the data, and then basically right sibling means basically the right child, right? Not the child, but you're capturing the sibling. So you have the data A here. What is the left child A? If you go back to the picture, the previous picture, you can say left child of A is B, right? Okay. Now B has siblings. Siblings are C and D. So now, if you go back to the slide here, you can see B has siblings C and D. If you follow the principle, B has a left child E, E's sibling is F. Okay? So we can continue. Right? So that's what we are doing in the case of a representation of a tree and left child, right sibling. Okay? There are many ways of representing trees. Okay, these are some essential. Now, from there, Give me a second. Can you hear me? Can you hear me now? Perfect. Okay. No idea why that happened. Maybe when the phone fell down, you could not hear me. So the height of a binary tree, complete binary tree, with n nodes is log 2 n plus 1. And there's some ways of proving these things, right? We are not into proving stuff, at least not in this class. Maybe the advanced class, maybe I'll do some proofs, but not in this class. Lemma basically means corollary, right? In Indian terms, we call it corollary, theorem and corollary. Now we covered binary tree representation through array and stacks and all that, but here I'm showing it to you in a slightly different perspective. The reason I'm showing you in a slightly different perspective is all of these things are building up towards ultimately showing you we have a problem representing it like this. That's why we need threaded binary trees. That is what we say. Okay. So if you have a complete binary tree and you want to represent it as an array, how would we do that? Okay. I'll jump a slide to show you how we did that in the class earlier. Okay. We said, remember, if you use array, we said that where would a node go, right? We took the numbering of the node in the tree to the corresponding index in the array, if you recall that. Okay. All that thing that we discussed is being said here formally. Okay. We are saying that if you have n nodes and you're representing sequentially means it's an array, right? Okay. Then when you take any node with index I, okay, how do you know what is the parent of I? Parent of I meaning it is at I divided by 2 if I is not equal to 1, because you always take the case of 1 node, 0 node, and more than 1 node, right? So the base case is 1 node. Okay. So if I equal to 1, I is at the root and has no parent. Okay. Now, if you're not in the root, then if you go to the intermediate nodes there, then you have to talk about the left child and the right child. So where is the left child at? Left child is at 2i. If 2i is less than or equal to n, you cannot exceed greater than n, right? Because array has array 1, 0 to n, so it has to be less than or equal to n. Okay? So these are some conditions that are there to which satisfy how, when a binary tree represents array, how do you know which is the root, which is the parent, which is the left child, which is the right child? So you need to have some formula. So as a computer science and engineering student, you need to know what that formula is. So this is what it is showing. But it is there for you to review, okay? Because it's very hard for me to figure it out from your syllabus whether you need to be told this level of depth. Okay. Okay. So the same thing that I showed you there is written here. Okay. So when you root is always at tree 0. Okay. For any node at tree n, the parent node will be found at index n minus 1 over 2. Simple formula, much easier to remember, right? For any node, the children of n will be found at tree 2n plus 1 and tree 2n plus 2. Very interesting how to come up with these formulas, right? You can always play with the numbers, but hopefully you're not asked in an exam what the formula is. So when we represent that in array, we saw in a slightly different form array, horizontal array. In this case, I'm showing vertical array, right? Because that's how the activation stack is built in the compiler or in the system. Okay. Now, when you do these things, one of the things that you notice is there's a lot of wastage of space, because if there is if there is a left or right every single time, the wastage of space would not be there. But we know that not every binary tree would have a left child and a right child, right? And since you have to use the concept based on the subscript of the array, you will see a lot of empty space. Especially that it is the case when you have a skewed tree. With a full tree, you will not have empty space. Everything would be taken nicely. But in the case of skewed trees, right, you will get a lot of spaces like that. And then the empty spaces are nothing but null pointers. I mean, there's nothing there. They're not pointing to anything. Okay. So, through some nice magic formula, you see that in this case, only k spaces will be occupied. Okay. Out of 2 raised to k minus 1 spaces, only k spaces will be occupied. That means we are wasting storage. Okay. So even though they are not being used, we have to allocate it and put a null pointer there. Okay. That is one problem. Okay. We are unnecessarily wasting space. The second problem is, once you build a tree like this, right? Now I want to insert and delete. Remember, the entire life is all about building the data structure and inserting and deleting things from a data structure. So whenever you are inserting or deleting, you have to move all these nodes to the right subscriptions, right? Subscripts. That's a big problem. It's rearranging, right? We kind of covered some of these disadvantages when we talked about arrays, right? Arrays versus linked lists. Okay? Rearranging stuff becomes a nightmare whenever you use the concept of an array. Now, how do we represent this in a piece of C code, right? So we said binary tree has 3 elements. One is the data, wherever the visiting. Remember, we did all the Inorder Traversal, and you know that. Data, and then left side, right side. We need to show left child, right child of the data. So if you look at the structure here, I hope your teacher taught you this in C programming. Type def is nothing but a synonym, right? We are saying instead of typing the full thing struct node star 3 pointer, this is represented as synonym by 3 pointer. Okay. Now once you do that, then how you define your node is node as data. You have a left child. Left child is nothing but another tree, right? That is the reason I say left child is of type 3 pointer. 3 pointers of structure node. It's a recursive definition, right? And then you have right child. So these 2 sentences here, type def sentence here, will give you the data structure to build your tree. Okay. Now, in this case, you're in essence building a dynamic array here, right? You're doing a malloc. We covered some piece of code there earlier too. We do malloc, which allocates memory. Then you assign the thing. You initialize the pointer. We did all that stuff in the previous chapter. Okay. Go back and refresh the chapter. You may want to review that. Okay. Now, once you have this, to show visual representation, right? You start at the root, and then you have a left side subtree, right side subtree. In this case, there is no right side subtree. Okay. Remember the skewed tree. Then you go to B. In that skewed tree, we had A, B, C, D, E. Okay. E was the leaf, and we build a tree, everything on the left side. But since the data structure shows both left side subtree and right side subtree should be shown null. So we fill out null. Now in the second case where it was a complete tree that which I showed you, It was not a skewed tree, it was a complete tree. Not a full tree, complete tree. It had both left sibling or left subtree and right subtree. So he filled out, okay, A goes to B and C, you can see the link. B goes to D, D has both, okay, and D goes to H and I. Whereas on the right subtree of B, it's stopping at E. After E, both of them are null. Okay. Then following along the same line, A goes to C, C has both left and right, you fill that. Okay. Now in the respective things, you see all the null values here. All that is wasted space. Actual links which are useful to traverse the tree are how many here? 1, 2, 3, 4, 5, 6, 7, 8. But if you count the nulls here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For 7 or 8 useful values, you have done 8 or 10 unnecessary null values. But still you have to allocate the memory for that. Okay. So that is a link representation. Okay. So problem is that the number of null links are actually more than the non-null part. Okay. Here is another example here, right? It shows a tree A, B, C, D, E, F, and you can see all the null links because the data structure says you have to show the data, and then the left side pointer to point to the left subtree, right side pointer to point to the right subtree. So that particular picture has 7 null pointers and 5 pointers. Total is 12 pointers. So when you generalize it, you will get this formula. A tree with n nodes, a binary tree with n nodes, not a regular tree, binary tree, will get n plus 1 null pointers and 2 n total pointers. Okay. Now, when you have a null pointer, the goal is, can we make use of the null pointer somehow? Because instead of keeping it useless, right? And then these authors propose the idea called, hey, we can make use of them. The way they are going to make use of them is they're saying they're going to replace all the null pointers by the appropriate pointer values called threads. Okay? They're no longer called pointers, they're called threads. So we are going to define what a thread is. Okay? Hard concept, but hang in there, you will get it. Okay, it's fun concept. And when you're learning a concept, you should also know what is the usefulness of the concept, right? Concept with no value, no applicability is useless concept. Okay? So we'll see the value of it shortly. Okay? Now, when you build a binary tree with such pointers, okay, it is known as the threaded binary tree. So you've got a binary tree. Each node is represented data, left subtree, right subtree. And regular binary tree would have the left subtree, right subtree. If there is no right side subtree, then you put the value as null. So in order to replace those nulls with certain values, we invented threaded binary tree. Okay. Now, since it's a slightly different concept from standard pointers, we distinguish between normal pointer and a thread. Okay. So now, you take the same node again, you're adding 2 more fields to the node. Okay? You have these 3 which are already there, which we know. Left child, data, right child. Now you're adding a left thread and a right thread. Okay? Now once you add these 2 fields, then you have to slightly look at your logic, right? 1 second. I should say good morning, SVECW. So then you can see here, if the left thread of a particular node P is equal to 1, okay, then we are saying left child of P is a thread pointer. So you are interpreting the value of L thread, and based on that, you're determining whether there is a left child or not. So if it is a thread, that means it does not have any more subtree. If it is not a thread indicated by 0, okay, the left child is a normal child. Normal child meaning it has its own subtree. Okay. Okay. Again, it's still abstract concept. Let's see how it looks like. Okay. Now, since we just like similar to pointers, we can use one-way threading or in a two-way threading. Okay. So all that is still abstract knowledge for you. Let me get to the main thing. Okay. So one-way threading here. Let's look at the example. So all of a sudden, it becomes a little tree becomes a little bit more complicated. So you have a binary tree of A, B, C, D, E, F, G, H, I, J, K, L. Okay. So from B, if you go to D and D, right? So there is nothing to the right of tree, to the left. Same thing with respect, whereas with respect to E, you have something, a left subchild called F. Okay. Similarly, you interpret the rest of the things. Okay. And then he's taken Inorder Traversal, and he's using a thread to point to the node above in some order. Okay. Now, in this case, where the thread is pointing to corresponds to the Inorder Traversal. Let me go back here. Okay. So if you want to, in this case, of course, the tree is going to be, Inorder Traversal will be D, B, F, E, right? A. Then you go to the right side, G. Well, in order means visit the node, from there visit the left subtree. After you print the display left subtree, then display the node and then go to the right subtree. So depending on the traversal, he is going to fill the thread values accordingly. I don't know if I should give you a quiz on post-order threading. Okay. Now, if you do a two-way threading of a node of a tree, a thread will appear in the left field of a node and will point to the preceding node in the Inorder Traversal. Okay. Furthermore, the left pointer of the first node and the right pointer of the last node will contain a null value when T does not have a header node. Okay. Now again, this is all theory, right? Let's see how it looks like. Okay. So here is the tree representation, which is a threaded binary tree representation. Not an easy concept. It will take some time for you to practice. I can put some practice homework for you to practice this one, okay? Assume let's pretend for a moment we understand that. Again, remember it's a formula, right? The idea is, instead of keeping them as null pointers, point them back to some other node in the tree. And where you point them back is reflected by whether you want to do a single thread or a double thread, and whether you want to achieve an Inorder Traversal or a pre-order or post-order. So there is certain framework as to that determines the values of those threads. Okay, that is the essence of it. The details here, once we practice, we'll get it. Okay. Now, why are we doing all of these things? It looks more complicated, right? Why did we make our life so complex? By introducing the concept of thread. Let's look at that one, right? I'll come back to this slide a couple of slides. Why do we do that? I'll come back to those slides, right? This is why we do that. There are certain advantages, right? The traversal is faster, okay, than of its unthreaded version, because a threaded binary tree, when you implement it non-recursively, right, you don't have to worry about the stack management. Remember how in stack, every time, depending on whether you see an operator or operand, you have to go do pops and pushes and all that, right? All that is going to take time. Whereas by using the concept of threads, you are speeding up the execution. Okay. Whatever concepts are given in data structures, these things, they are given for two reasons. Number one, try to keep approaching the log to n algorithm speed. Number two, reduce the amount of space. Okay. So in this case, the advantage is the execution time is faster. Okay. That is one big advantage. Okay. This is a real big advantage. Now, since you connected the nodes, not only going from top to bottom like in a hierarchy, you are now connecting the nodes going from bottom up, right? From the leaf to the root through thread. Right? So that means we can determine the predecessor and successor nodes from any node easily. Okay. Now, if you do not have the thread, that's what this sentence says. In the case of unthreaded binary tree, that task is more time consuming and difficult. Why is it difficult? Because you have to literally traverse and evaluate whether you have that connection or not. Whereas here you already know it because it is saved in the thread. Okay? So to do the predecessor successor type of evaluation in a binary unthreaded tree, it's going to take longer. Okay? So where we use the stack, right? And then we know the upward pointing, downward pointing, and so on. Whereas once you give a thread, you have the upward pointing information right there for you. You don't have to compute; it is there. Okay. So without having to use any stack mechanism, you can use the concept of threads to do the upward pointing. Like if I want to know who the predecessor of a node is, I can do it faster. Okay. Very technical reasons, right? Generally, in a beginning class, when you're talking about trees and binary trees and so on, I really don't talk about threaded binary trees. That's more a concept for my advanced class because you're not really writing code related to these things, right? In my advanced class, you do. But your syllabus says we have to cover it. Okay? So if I have to summarize this one, a couple of other advantages. Now any node can be accessible from any other node. Okay? And you can read this sentence here. Threads are usually more to upward, whereas links are downwards, right? So left side, left subchild, right subchild, they're always going from the root. If you have a need to traverse from going from the leaf towards the root, then you follow the threads. Okay? You don't have that in a regular data structure of binary tree without threads. Okay? That is what the essence of it is basically. We use threaded binary trees to eliminate the wastage of the links, null pointers. Since the space is already allocated anyway, we are saying why not use the space? And the way we are using that null pointer space is by showing an upward link. So that way, if you have to traverse the tree bottoms up, following the thread would allow you to traverse the tree quickly. Okay. Questions, comments? Where there is an advantage, there is some disadvantage. Okay. Anything to do with insertion and deletion from a threaded tree is very time consuming. Because now you not only have to modify the left subchild, right subchild, you have to modify the threads too. Remember, threads have rules. How do you build the thread? Okay. So you have certain disadvantages. Okay, let me pause here quickly to answer any questions. I'm not giving any particular big exercises for threaded binary trees. Since it is there in your syllabus, I covered it. Okay? The maximum, I don't think you would get any big questions on this other than that. Okay, tell me the concept of a thread. Why do you need it? Okay. So if I see a question, if I say I do need a concept of thread because there, if I build a normal binary tree, okay, I will have a lot of nodes with, and the normal binary tree you represent it as the following. You have data, you have left subtree, right subtree, links to left subtree, right subtree. Okay. Now it turns out most of those links are null. Okay. The actual links which have value is that number is less than the other links which have no value. So to utilize those null links, we invented the concept of threaded binary tree. Okay. So in the threaded binary tree, you have some kind of a formula to replace that null link with the predecessor of a node. Whatever node you're considering, that thread is replaced with the predecessor. The question then becomes is, where would that thread point to? Okay. It's not pointing always to the parent, right? It shows where it needs to point to. Okay. Now, okay, so what is the big deal about pointing it to some? Have to, for a given node, if you have to do upward traversal, meaning you have to find the predecessors, the threads enable you to arrive at that solution faster. That is the overall concept of threaded binary trees. We'll do one or two examples as homework. I'll put in the community and you can do it. But beyond that, we'll not write any piece of code, or I'm not showing any code. But that is fine. Okay, 3-minute stretch break. Okay, 3-minute break now. Stretch yourself, get up, stretch, get some water. I'll go get some water. Okay, I'm back. So the question was how to represent threaded fashion. I think it gets messy, right? It's still an array. Okay. You have seen the null point. I think it basically becomes complicated, right? So I think that, yeah, the way I write it is once we implement it in code, the traversal becomes faster. The only reason can you hear me now? I dialed back in. Yes, perfect. Okay. So whenever I'm muting and going back into mute, I think it's somehow disconnecting, I think. Okay. So as I was saying, I mean, it is still an array and you still use the concept of expand the concept that I mentioned to you, except now it has more elements, right? In addition to the left subtree and the right subtree, you're adding two more fields, right? Called the left thread and the right thread. That's all you're doing. But the entire framework of how we showed it in the array would still remain the same. But it does get messy. Let me show you what I mean by that. Let me share the screen here. I pulled in another example for you guys during the break. Let me show it to you, and it clarifies your concept too a little bit. Bear with me for a second. So if you look at the binary tree here, right? Just to clarify the concept a little bit more, you have a binary tree here. To convert this into a threaded binary tree, how do you form those threads, right? I kind of showed it, but I skimmed through it. But this example, I think, brings it out better. Remember, I skipped a few slides. Okay, I think it's a little bit too deep, but here is a simpler example. So you have a binary tree. You want to convert that to a threaded binary tree. We talked about Inorder Traversal, the way the links are done, and the way it is done is based on Inorder Traversal. That was the example that I showed you. So first we have to find the Inorder Traversal of the tree. So by now you know what the Inorder Traversal of this tree is, right? You visit the node, you don't print the value. You visit the left subtree, print the value, go to the right subtree. So if you remember that Inorder Traversal algorithm, this is the order in which the traversal is going to display. H, D, I, B, E, A, F, J, C, G. Correct? That's Inorder Traversal. So you're visiting node A, going to B, visiting node D, then going to H. Say no more visits, right? You print that. Go back and print D, then go to the right subtree, that's where you get I. So go back above, print B, then E, and go back above, print A. Okay. Now when you come to the right side here, you keep going all the way down, then you can see how you get to F, J, C, G. Okay. Now to convert this here, okay, this is the process. We are doing it using, in this case, linked list, right? You go to the chi, E, F, J, G are left child pointers are null. Okay. We are going to replace the null by the address of its in-order predecessor. Okay, that is a key part here. Let me highlight that one here. Again, I don't think these are the type of thing that we will have to memorize, right? Sorry for the small print here. So for all the left child pointers, we are doing it based on that one. Okay. So you're doing I to D, okay, E to B, and so on. You're doing an in-order predecessor. So the reason why you know the in-order predecessor is on the previous slide I showed you what the in-order traversal is. So wherever you have left pointer, which is null, you point to its predecessor using this in-order traversal path. Okay. Now, whereas if you look at the node H, it does not have its own in-order predecessor. Okay. So if the node H in this case has no predecessor, in-order predecessor, because it's a leaf node, right? So in this case, what do? You point it to the root. That's what the rule says here. So point it to the root node A. Okay. Now, similarly, when you have nodes H, I, E, J, G, right child pointers are null. In the case of right child pointer, this null pointer is replaced by address of its successor. So in the left case, you called it predecessor, but in the right case, you're calling it the successor nodes. Okay. Now, what happens if the node does not have a in-order successor? You point it to the root node. So basically, there are 4 rules here, right? 2 rules correspond to the left side and 2 rules correspond to the right side. So by doing those things, you build a tree which is all of those things. Now, in this case, the array data structure would have 4 elements. That's all it is. Okay. Becomes a little bit messy, but that's what it is. Okay. How it looks like based on this at the end, right? After I cover a little bit of binary search trees, I'll let you actually draw the pointers based on this exercise in the class, okay? So let me go to the binary search trees. Okay. So I made you do some binary search tree, if I remember, in the last class, did I not? Okay. Now it turns out we didn't cover heap, but basically we need the binary search trees because heap is not suited for application in which arbitrary elements are to be deleted. Some complexity analysis done, and we do need that. All this first paragraph is saying is, right, is justifying why we need binary search trees. Okay, in our own educated layman's way, we said why we need them, right? If you have an unordered stuff, if you make it ordered binary search tree, when you're searching for an element, it cuts down your search time by exponentially, log, basically, right? So depending on the tree search, the depth of the tree, it's log 2n. Okay, that is the reason why we need a binary search tree. There are a lot of other reasons. That's what this is trying to show you when you talk about heap and all that. Okay, so ignore that first part for now. Okay, now definition: every element has a unique key. Okay, We have to see what this key is. I'm just giving you the theory part, right? We'll do the practical part shortly. Okay? Now, the keys in a non-empty left subtree, okay, are smaller than the key in the root of the subtree. Okay? So that means as you're traversing the tree from the root, left of that root has values less than the root, right of the root has values greater than the root. So it is an ordered tree for you. When you have an ordered tree, when you are searching for a key value, then all you have to do is whatever node you're visiting, you say, hey, the key that I'm searching for, is it less than or equal to or greater than the node that I'm there at the moment? So that is every iteration, you're cutting down half of your search space. That is what a binary search tree is. Okay. So let me show you the example here. Okay. So left side, you have 20, right? So if you go look at the left side here, 15 is less than 20. Now left of 15 is less than 15. 25 is greater than 20. You get, so you see it's right of 20. Okay. So you're building these search trees following the principle. Okay. So you have, I like this medium, smaller, larger. Smaller is always less than medium, larger is greater than medium. Okay. So when you have a search tree like that, when you're searching for search 25, search 76. So when you're searching for 25 value here, you're starting at 44. Okay. Where is 25 here? Do I see 25 anywhere? You will not find 25, right? Because there is no 25. But the way you do that is, you say, okay, I'm searching for 25, so 44. 25 is less than 44, so you go to the left side. Okay. Now 17. 25 is greater than 17, so you go to the right side. See the black lines that I'm following here, okay? Now I complete 25 to 32. 25 is less than 32, so I come here, left side. Now I say 25 is less than 28, so I come to the left. 28 is pointing to null. Okay? So I can say, I can tell the system, hey, the value is not there in the tree. Remember, we covered this even at the very beginning. You probably may or may not remember. I said, hey, if you draw it as a tree, it's faster. If you have to put all these elements in an ordered array, you would have had to search 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 elements you have to search. Right? Potentially, if it's an unordered array. By putting them here, you are able to say that in how many steps? First comparison, second comparison, third, fourth comparison. In 4 comparisons, you're able to tell that 25 is not there in the. So how did you find 76? You follow the red line. Okay, one was the blue. I said black, sorry, blue. The other one was in red. So follow the red line, go to 88. 76 is less than 88, you go to 65, follow the red line. Now 76 is greater than 65, follow the red line, go to 82. 76 is less than 82, you come here. You found it. Okay. Pretty straightforward, very nice. Okay, now how do you, there's some piece of code that I gave here. Again, it is there. You don't have to, I don't have to teach you this code yet, but this is how you write the search tree code here, pretty straightforward. But I'll read out a couple of, I'll point out a few things here. If you look at the first if statement on the top of the page, if not root, return null, meaning, hey, there has to be a tree to do, right? Assuming there's tree, then you go to the next if statement. Next if statement is, the key is equal to root. Double equal to means it's equal to, right? Root dot data. When the values match, then return the root. Okay? If not, then the third if statement. If key is less than the root dot data, Then recursively you call the search function with the root of left child. And then pass it. So if it's greater than the root value, then you say return search root of right child key. Okay. So very, very simple to do the searches. That is the advantage of a binary search tree. Now, this shows some piece of code for inserting into a binary search tree. Okay. Now, again, the code is there, but I'm not going to go through the code. If you guys want me to go through the code, I'll be happy to do that in the next class. Okay. We actually write these codes, these things in my advanced class. Okay. Now, when you delete from a binary search tree, okay, what happens, right? This is the beauty of these structures like this, right? That whenever you're inserting, deleting, then you may potentially rebuild the tree. Okay, that is what this is showing. If you delete a leaf, that is one aspect. Case 2, if you're deleting a child, then you have to delete and change the pointer to that child. Case 3, 2 child, meaning either the smallest element in the right subtree or the largest element in the left subtree. So whenever you're deleting something, the pointers do change, right? Because that node is no longer there. You have to manipulate the pointers accordingly. In my advanced class, when you write the code, I'll make you do these things so that way you can see the code in action, whether your code is working correctly or not. You can see here how he's showing an example where on the left you see a tree, and what is he trying to delete? He's trying to delete 60. Okay? Now, if you delete 60 pictorially, what should go next to 60? Instead of 60, what should 40 point to? You would think that 40 would either point to 50 or 70, but that's not how it works. Because there is a way that this tree is built, right? Whether the key value is greater than, less than, things like that. If you delete 60, you are redoing the full subtree under 60, because that is the root of that subtree. You have to apply the algorithm of the based on the rules of how you build the binary search tree. As a result of that, the next 60 is replaced by, as you can see, 55. Okay. Now, when you are doing this, you can see the rules are met, like 50 is less than 55, so it is on the left side. Okay. You would simply think that, oh, I'll remove 60, I'll put 50 there, and instead of 50, I'll put 45 under 50. It doesn't work like that. Okay, so that is high level. Again, I'm giving you the concept, but not the full algorithm. To write that piece of code is pretty complicated, by the way. Looks simple, but not easy. Now, I gave you a quiz earlier. So here is a quick concept. Height of a binary search tree with n elements. Okay. Potentially, it can become as large as n, right? If you have a skewed tree, as we have seen at the beginning of the class, it can become as large as that. Okay. As the slide says here, bottom line is, in general, for binary trees, you can show that when insertions and deletions are made at random, the height of the binary search tree is going to be log 2n. Okay. Now, when you get the search trees, the worst case height of log 2n, they are called balanced search trees. Okay. We did not see some of these things. We'll see them in the next few classes. Okay. But in general, trees are good. Remember that. Okay. And then there's some time complexity. We'll come back to time complexity later. Too many advanced concepts here for you. Okay. Now, typically what we do in the advanced class, we don't stop there. We get into a couple of other tree structures to address the concept that when you have a worst case is skewed, right? You get order of n. So to get to log of n, we have a couple of other trees called AVL trees, 2-tree trees, and red-black trees. So if time permits, I'll try to tell you what these are. in this class itself, some high-level introduction. But otherwise, this is as much binary trees as you would get. Okay. Questions, comments?